Welcome to Lecture 1.4 MATLAB as a Calculator for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you'll have an understanding of a simple calculator-type application for programming, how to relate engineering problems to programming, how to use the command window for basic math, how to solve the example that's provided as motivation at the start of this lecture, and an introduction to vector arithmetic in MATLAB. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. Advanced topics in computing include numeric simulations and machine learning and quantum computing, robotics, and even more. But before entering any of those fields, you must be capable of basic computation. To address this, we'll consider a simple mechanics problem that you should already be familiar with. Our example: how far will a projectile travel given its initial velocity and launch angle? Don't worry, I will do all of the math for you. You can focus on just learning how to code. The solution for this problem utilizes just two kinematic equations. The first one that we will use is that v sub y equals the initial y velocity plus the acceleration times the time elapsed. In this equation, the only unknown is the time t. We know that the initial y velocity is calculated as the sine component of the initial total velocity, and that the y velocity is 0 at the peak of the trajectory. And we know, of course, that acceleration is negative 9.8 meters per second squared, as that is the acceleration due to gravity on Earth. These three things allow us to directly solve for t later. Then the second equation is delta x equals the initial x velocity times the total time elapsed. Delta x is the only unknown in this equation because the time t is found from step 1, and the initial x velocity is calculated as the cosine component of the initial total velocity. Both steps of this problem are really just solving an algebraic equation. This is perfect for a script employing basic computation. So, after covering the basics of computation in this lecture, we will circle back to this problem and solve it using programming. MATLAB is great for doing simple math like a calculator. For example, take the following operations. First, we can define a variable a, set it to 5. Then we can add 2 to its value and store that in the variable b. And then we can add a and b and subtract off 2 to define the variable c. Similarly, multiplication, division, and exponents are also straightforward with their respective operators. Again, start by defining our variables. These are the same as the ones defined on the previous page. Then we introduce multiplication and division between a, b, and c. And then we can introduce exponents with the caret operator. These simple demonstrations highlight your ability to do low-level arithmetic in programming. To compute the value of arithmetic expressions, MATLAB follows the PEMDAS order of operations, just like in normal math. Parentheses wrap around bits of code, which is denoted as x here, and their contents are computed first. Exponents, which use the caret operator, are computed next, after all parenthetical expressions have been addressed. Then multiplication and division, which use the asterisk and backslash operators respectively, are computed. And finally, addition and subtraction, which use the plus and minus operators respectively, are computed last. To illustrate the applicability of PEMDAS, let's look at some examples. We first take a plus b divided by c without any parentheses. According to PEMDAS, the term b divided by c will be computed first because division is higher in the hierarchy than addition. The result is 5.7. We then add parentheses around the addition term, which forces MATLAB to compute a plus b before dividing their sum by c. This results in 1.2. And finally, if we add an exponent inside of the parentheses, then a squared is computed before adding b. Then once all operations within the parentheses are complete, the whole term is divided by c, which overall results in 3.2. Armed with this knowledge, we can tackle the problem that is posed at the start of this lecture. Recall, how far will a projectile travel given an initial velocity and launch angle? Step 1 is to solve for the time t at which the projectile reaches its peak. As we discussed earlier, we know that in this equation v sub y is 0, so we can algebraically rearrange this equation as follows, and then we know that the initial y velocity, the numerator, was simply the sine component of the initial total velocity, and that the acceleration is negative 9.8 meters per second squared, which, when substituted, gives us this final equation. Step 2 is to then solve for the distance that the projectile travels using this equation, which was discussed earlier. Here, recall that the variable t found in step 1 actually refers to the time to the peak of the trajectory, which is only half of the total flight time. Therefore, it is multiplied by 2 in this equation. This gives us the following two equations. Both of these are easily written as arithmetic operations in code. For the sake of this example, we'll arbitrarily pick that the initial velocity is 10 meters per second and that the launch angle is 30 degrees. So let's define these in the code. First, we write a variable to store the initial velocity, and we call it such. Then we make another variable to store the launch angle, and again we name it appropriately. And finally, we write a third just to store the value of gravity's acceleration. Then to simplify later steps, let's define a variable to store the initial y velocity as the sine component and one to define the initial x velocity as the cosine component. Note that the d on the sine and cosine functions denote that the input is using degrees. If you omit the d, it is taken as radians. Then, using the equation denoted as step 1 earlier in this lecture, we can solve for the time to the peak. Note that in this equation, I place parentheses around the division term. This is not strictly necessary, but it does help to convey the equation better. It is found that the value of t is 0.5102 seconds, which again represents the time to the peak of the trajectory. And finally, the moment we've been building towards, the total distance is found by implementing the equation denoted as step 2 earlier in this lecture. Again, the parentheses here are not strictly necessary, but they do help to convey that the term 2 times t peak is distinct from the multiplication step with the velocity component. The total distance traveled is found to be 8.837 meters. Now, to pivot slightly, in addition to basic computation, it is helpful to understand how to work with vectors in MATLAB. In mechanical engineering, we use vectors for all sorts of things, like the application of a force, an object's momentum including both linear and rotational momentum, the velocity field of a fluid, and so many more things. In math, we represent Cartesian vectors with a component along each of the axes, where a vector v would have components v sub x, v sub y, and v sub z. In code, we define arrays to store the same information. Here we use square brackets as a wrapper and commas to separate each element in the row vector. Importantly, this vector is stored as a 1 by 3 array, which means that there is 1 row and 3 columns. The three most basic vectors are the three unit direction vectors. I hat represents the x-axis, j hat represents the y-axis, and k hat represents the z-axis. Hopefully these are all familiar from physics, calculus, and other classes, but following the format from the previous slide, these can be written in code as follows: I hat, j hat, and k hat. Now, with three unit direction vectors defined, multiples of each can be added together to construct any three-dimensional vector. Again, we have the three unit vectors, and we can define a new vector v as the sum of 3 times I hat, 2 times j hat, and 1 times k hat for an arbitrary choice. This defines vector v to be the vector 3, 2, 1. And in the same way, non-unit vectors can be added together as well. We define the vector u as 1, 2, 3, and vector v as 3, 2, 1. If we set the vector w equal to their sum, Each corresponding component of both vectors is added together, which results in w equals 4, 4, 4. Now, a natural question from this is, can vectors be multiplied just like regular numbers? We can experiment with this, and we will see that multiplying the vectors u and v as defined previously with the asterisk operator will cause an error. The error reads, error using asterisk, incorrect dimensions for matrix multiplication. Check that the number of columns in the first matrix matches the number of rows in the second matrix. To operate on each element of the matrix individually, use times, period asterisk, for element-wise multiplication. Ignore this last sentence for now. We will come back to what that is referring to in a future lecture. Now, as the error message explains, two arrays can only be multiplied when the number of columns in the first array is equal to the number of rows in the second array. In the case of vectors specifically, they can be multiplied together in the form of the dot product, also known as an inner product, as follows. A row vector times a column vector results in a scalar output. With this information and knowing that u and v as defined previously are both row vectors, we have to transpose the vector v in order to use the asterisk operator to compute the inner product. Here, the inner product of u and v results in the scalar 10. For 1 by 3 vectors, this is equivalent to the dot product, which produces a single scalar value, if you remember from your previous classes. In contrast, multiplying a column vector with a row vector, which is known as the outer product, produces a matrix. With this information, and knowing that u and v, again, as defined previously, are both row vectors, we have to transpose the vector u in order to use the asterisk operator to compute the outer product. This produces the following matrix: 3, 2, 1 in the first row, 6, 4, 2 in the second row, and 9, 6, 3 in the third row. So, back to the original question. Can vectors be multiplied together? Yes, they can be multiplied, but their dimensions must match correctly, and they have to be oriented properly for it to work. Now, in summary, this lecture covered simple arithmetic examples for programming. In this case, it was a simple physics problem that only requires a series of algebraic calculations. These are perfect for writing a little bit of code. How to relate engineering problems to programming, and that comes in the form of recognizing that a problem only involves basic computations at this level. That makes programming a more attractive approach to solving it rather than, for example, using a calculator. How to use the command window for basic math? Well, you can define variables and execute arithmetic operations in the command window, and each operation is entered and executed in order. Then we went back to the example provided at the beginning, and we found that the series of algebraic calculations required for that basic application are executed together as one script to progress through solving the problem. And then we learned a little bit about vector arithmetic in MATLAB, where vectors can be written as 1 by 3 arrays and then added and subtracted from each other on an element-wise basis, just like in normal math. They can also be multiplied to perform the inner and outer products as long as their dimensions are oriented appropriately.